Thank you very much. Thank you, Amarnath. Thank you, Tracy. So I know I'm the last thing between now and a break, so I'll try to keep this brief. This is actually a project that we presented on last year as well, so we're near the end. And so I will primarily focus on the progress we've made in the last year since our last presentation, but I'll just briefly touch upon what had been the progress up to that point. So we're going to be kind of switching gears, I feel, a little bit, not too much ground motions here, just one slide, of course. But we're going to be talking about gravels. And so why? Why do we care? Well, they're very challenging materials to characterize both in the lab and in the field, mainly due to the size of the grain. So basically, you cannot use conventional laboratory testing devices or conventional field testing equipment to test them and therefore characterize them. However, they're still present in nature. They can make up the foundation materials below critical dams. They can be found in reclaimed land behind ports and quay walls. They can be basically anywhere other soil can be. And up until fairly recently, there were a lot of assumptions and a lot of hand waving in terms of, the properties that we would use, depending on whether we were doing a simplified or a more advanced analysis approach. And so this peer project is part of a much larger project that I've been working on with my group for the last several years and trying to really make progress in this characterization. We're going to focus primarily on the liquefaction evaluation of these materials, and we're going to be looking at it from two ways of the laboratory testing and the numerical modeling approach. Should I use this one? Is it not advancing? Oh, my screen. Okay, got it. Okay. Okay. Let's see. Okay. Okay. I think I figured it. Okay. Okay. Okay, so as I was saying, this is part of a larger project. I love really applying an integrated approach to problems because I feel that all aspects have something to contribute in better understanding these materials. As I mentioned, these materials are difficult to characterize. So how have we been able to do it? So we've been very fortunate to have a prototype laboratory testing device, the device that you see here to your left. We basically built the device GeoComp, and that was while I was still at the University of Michigan, and then when UC Berkeley, we transferred the device with us. And so this device has the characteristic that it has the capability of testing large grain size materials because it has a much larger diameter than conventional devices and can apply both monotonic and cyclic tests. And so that has been the premise basically of the laboratory testing. This is how we've been able to get most of our data. And as I said, this was the focus of the presentation last year. Today, what I'm going to be focusing on is the back analysis of case histories, which is the second component of the project. So we have had, of course, a lot of cases where these materials have in fact liquefied and have impacted critical infrastructure. And so the case study that I'm going to be talking about today is from New Zealand. And of course, as I mentioned, there's other components in the kind of long-term project. We are looking into 3D discrete element modeling to try and understand the response more at the micro level as well, the impact of fabric, particle morphology, angularity, aspect ratio, that sort of thing. And we have also been kind of developing procedures so that we can use some more conventional field testing equipment to help us, again, with better characterization of these materials. So one of the kind of more important outcomes of the laboratory testing study was that we had gravelly soils shipped to us in New Zealand. And so we are testing the actual material that I'm then going to be presenting the dynamic analysis for. Of course, it's going to be reconstituted in the lab. That's what is always the case with cohesionless material. But we do target different relative densities, right? And we do this in a very systematic way, having full control in the lab, unlike what happens in the field. And so, of course, this very nice figure represents, a couple years of worth of testing and various other conditions, but then it can all come together and summarize this very pretty figure. But basically what we're showing here is something that we're typically interested in when we're looking at soil liquefaction. We want to know the relationship of the cyclic stress ratio, which is essentially your demand, the loading that's coming from your earthquake, like a series of equivalent uniform cycles of loading, versus that number of cycle, right? So how many of these cycles do you need to liquefy? And so you create this relationship, and this line basically represents different levels of relative density for different materials. And these lines are going to shift again for different materials, but even for one material for different relative densities as well as other parameters. So here we've targeted 3 different relative densities, kind of the looser one at 45%, medium dense 65%, and a dense gravelly soil at 85%. Typically like to do loose and dense, but the 65 was targeted on purpose because all the indications from the field characterization in New Zealand indicated that that was the more representative relative density for the natural deposits. These curves are what you calibrate your constitutive model when you're trying to do dynamic analysis with liquefaction, okay? Now, most people do these liquefaction analysis for sandy materials. And because these materials have been tested and tested and tested and tested, we have a lot of these curves. And so the developers of the models with these sands in mind have developed really good generic parameters for you to use, and typically have really good guidance in their manuals on how you may need to adjust depending on some differences in your material. But these curves look very different for gravelly soils, right? And so we have been able to have, develop these site-specific materials curves that we can then calibrate the constitutive model to. And so this has been the contribution of the first part of the project. Now, moving on to the second part that's going to focus on the dynamic analysis, I do want to kind of just familiarize you a little bit of the area. So this is New Zealand at the upper left. We see basically where the North Island meets the South Island, and we see Wellington there. We're going to zoom in at the bottom left where we see the central Wellington and lower Hutt, Petone. We also see the various faults. The red, thicker solid line is the Kaikoura fault that actually was the one that produced the earthquake in 2016, but of course there's other faults around. And then finally on the right, we also see a little bit of the geology that will affect a lot of things that we're going to be talking about, in addition with the red triangles that represent the strong motion sensor stations. Okay, and so this is where we have information. So as you can see, we actually are going to have a lot of information of the movement and the shaking. Zooming further into the port of Wellington, or center port as it's known, we see in both figures, you see basically all that kind of almost square rectangular looking shapes, reclaimed land. That's why it looks like that, right? We've created it like that. And then we have basically a stratigraphy that I'm going to show you in a minute. But on the left, what we see is basically the mapped area following a reconnaissance after the 2016 earthquake, where they have mapped where we saw different types of ejecta, cracks, and basically surface manifestation of liquefaction. And so we also had damaged structures and then a couple of buildings that had to be demolished. And so we see basically a really prominent spread both of gravelly ejecta, which is kind of this brownish color, the sandy ejecta, a little bit less so with yellow. And then we also have, like in blue, areas where you had both water with sand silt ejecta trace. And so, as I said, again, pretty spread out. For the first section of our dynamic analysis, we picked cross-section C prime that you see indicated there. And then we are also planning on adding 2 more cross sections perpendicular to that. We have several open fronts, and so we want to understand basically the responses as best as possible, because there were lateral displacements in all 3 of these directions. And so we want to be able to capture that. Now, for this specific case, there was more data than you would typically have for your dynamic analysis. So that's good. There was a lot of site characterization, shear wave velocities, CPTs, cone penetration tests, laboratory data, of course, which was our part of the overall study that we conducted with the material that was shipped to us. There were a lot of observed and measured deformations thanks to the gear, reconnaissance, and follow-up subsequent report. And of course, Misko Kupinovsky, who's also collaborated in this project, has done a lot of work since the earthquake and provided cross sections for the subsurface stratigraphy. Before you get to the dynamic analysis part, it's important to do that for a representative ground motion. And so picking that ground motion is also a process in this project. As I mentioned before, there are actually several recordings. So on that aspect, we're at an advantage. On the other hand, you can tell from the various recordings that there's clearly effects of the soils that lie underneath a lot of these stations. And so you clearly see these changes, which is great when you're a geotechnical engineer. It kind of speaks for soil response, right, and site-specific analysis. But when you're trying to identify the motion that you will then involve so that you can use it for your own analysis, you don't want these effects there as much as possible, right? Because then you're kind of carrying it through your analysis and you don't know, if what you're seeing is because of that or because of other factors. So basically the exercise we did is that one of the stations is considered a rock motion. And so, but it's a little bit further away. And so what we did is we used that motion and our proposed subsurface stratigraphy, and we saw basically how close we were able to match some of the other recordings, right? So that we could calibrate our stratigraphy as well as our input ground motion. And so with all that said and done, we ended up using basically the POTS recording from the rock site recording because it produced good matches to the other two sites with the proper deconvolution, of course, so that it can be placed as a within motion. This is the underground stratigraphy. Basically, the material of interest to us is going to be kind of the second down where it says the gravelly reclamation. So that's where this gravelly fill is placed. And of course, there's going to be variability in this material, right? So there's going to be pockets where there's more sand and less gravel. There's going to be pockets where there's more gravel and less sand and everything in between. So basically, there was a lot of sampling that took place, and there is a range of gravelly content from between 40 to 85%. Right. And so you're going to have this distribution because it's a fill. You do have that kind of almost, I don't want to call it a pocket. It's kind of a layer that tapers out the sandy reclamation fill. And it's a little bit unknown exactly where the transition happens. And then we have the marine sediment that was there before and the Wellington alluvium below that. And so for our models and our parameters, we basically want to be able to model the possible liquefaction within the gravel and the sandy reclamation fill. And so for those two materials, we use the PM4 sand model. For the sandy reclamation fill, of course, we go with the more generic sand properties, but then for the gravel, we calibrate to the curves that I showed before, as well as for the post-liquefaction strength that we have developed from our lab testing. And for the non-liquefiable soils, we use for now just a simple Moore Coulomb model and used some generic values based, of course, on field characterization. So this is a busy table, but basically just kind of summarizing all of these parameters, as well as the phases that we use in our analysis. We use the 2D FLAC dynamic finite difference program. And so you see the variation in the properties there. So this is what the mesh looked like. So the model is quite long. And so you just see some snapshots of the two edges. It was really important to us to kind of model the entire cross section as one because there was lateral displacement observed on both sides. And so we wanted to be able to reproduce that without having to do any kind of symmetry, basically inject our own symmetry on the model and kind of splitting it down in half. As a result, it takes a lot of hours to run. But we just feel it's more representative being able to do that. And so you see what the model looks like. So as I mentioned, we have our laboratory test developed curves for the gravel. Basically you just see, how the curves that we selected compare with some of the other curves. What we see on the right, which is really more important in this slide, is a prediction of what of the capacity that these materials exhibit against liquefaction. Those are the blue, green, and orange curves that come from a variety of models. And then red is basically the demand. So the best prediction we can have given the recordings that we have. So it's a pretty good prediction of what was the demand. So you see that we expect liquefaction to happen in these gravelly deposits. So it's really about being able to capture that in the 2D model and being able to see what that meant in terms of the displacements. And so if we can kind of look at the top figure, which is the results for the excess pore pressure ratio. So dark blue is bad. It means that you've hit excess pore pressure ratio of 1. What that means in liquefaction is that basically your excess pore pressures are matching your effective stress. And so reducing basically that vertical effective stress essentially to 0. That's the worst case scenario, but essentially your material can be considered to have liquefied, meaning it will produce significant deformation even at RU ratios lower than that. So essentially we know that for these materials, if you're anywhere above 0.65, you're kind of really close to unacceptable deformations. And so we see that the entire area of the gravel deposit is affected, but not to the same degree. So there are areas where the RU is basically the greenish color, which is a 4-5, right? So that material may be considered to be stable, but we do see the blue pockets and where they have developed. And this is just a cross section of the stratigraphy underneath, just to kind of remind us of where we have the different materials. And then this is where we show basically where the material that liquefies, you assign the residual strength right after it liquefies, because that's a next critical step. You can't just wait, you can't basically just stop your analysis at the RU. You have to look, especially when you have open face, you have to assign then a residual strength. This is essentially the post-liquefaction residual, the strength, so that then you can capture the deformations appropriately. And so for that as well, we use residual strengths as supported by our laboratory data for the gravelly materials. And so when you apply those, this is what we see in terms of deformation. So if we can focus at the top figure for a moment, that's the lateral movement. And we go from right to left, kind of following the cross section that I showed you. And so the right is close to the right open face and the left is close to the left open face. With the different colored dots, we see observed and measured data following the earthquake. And then the red line follows the black dots that are flak results, okay? And so we see in terms of what we're trying to model, and given that this is kind of a class A prediction at this point, we haven't played with any parameters yet. So we did our absolute best from the get-go, then plug everything in and just run the analysis. And these are the results that you see. So from that point of view, I would say that it's doing a pretty good job kind of capturing, telling me basically where I'm expecting my displacements, a little bit better on the left than the right. We're under predicting a little bit, but this is going to be kind of the follow-up steps to try and understand, what the parameters control and whether realistically we can adjust them and be able to support that with the field characterization. Now, the vertical movement is a whole different story, and there's reason for that. So the vertical movement, we see good matches kind of near the boundaries of the open face, I should say, because the vertical movement there is primarily controlled by the lateral displacement, right? So you spread out, and so you settle. And so there's kind of correlation there. And so if we're doing well in the lateral, we should be doing good in the vertical on that aspect. But all the way in the middle, there was vertical displacement that was documented that is not captured by the model. Well, there's a reason for that, because all these vertical displacements are due to the volumetric settlement and settlement due to ejecta. This is not something that flak can model. Okay, so flak is a continuum. And so there's no way for me to be able to capture that. So then I have to go back using simplified procedures, right, and create predictions and estimates of what those volumetric strains or strains due to ejecta would have been for that middle part. And so we don't expect basically the match to be good there, because that's beyond what the model can capture. And so for our next steps, basically, we're going to be doing some parametric analysis for our dynamic for this model, basically trying to change certain parameters so that we see how sensitive the model is and, where, and then explain, hopefully the why, and try and see what we have to do to get the best fit with the observed displacements. So with that, I'll thank my collaborators and all the various funding sources. As I said, this is kind of a part of a bigger project, and thank you for your attention.
Any questions?
I was curious about the post-liquefaction residual strength. I think the sand, you can see the photos as a graph of the vertical effective stress. We use something similar for gravels.
Yes.
Can you
yeah,
repeat?
Yeah.
Yeah, so the question is basically how the residual strength selection compares with the process for sands, where it's basically as a percent of the vertical effective stress. And so it doesn't have to be, but because it's established for sands, we have done it that way as well. One of the problems with doing that is that once you've liquefied the initial vertical effective stress, which is typically your normalizing parameter, actually is no longer a good normalizing parameter, right? So the relationship is not linear, nor should it be. It would normalize perfectly with whatever the current vertical effective stress is, but there's no way to be able to predict that without running an analysis every single time. So we revert to the first one, that, it can be a bit problematic. So we've done it similar for gravels. What we've seen for gravels is that there is even more variability than what we see for sands in selecting that ratio. And so in the lab, we're trying to use particle morphology characteristics to see what that is controlled by.
Any other questions? Then I think it's time for break.
Yeah,
so
thank
much.
you.